Okay, so I will share the recording later, but please attend until the full session until 4:15. Okay, so okay, wait for a while. Okay, if you don't understand or whatever, please interrupt me because I may not read the Webex chat because it's difficult to see multiple screen here. Okay, so last week we have finished on this chapter 1, not the entire chapter 1 slide, but we already finished on the sorry, we already finished until here, okay, until this one. Am I correct? Until this one, right? Okay,
Yes,
good.
Doctor.
Okay, so we will finish this second part if possible. Okay, means we finish the slides. Okay, okay. So I proceed sharing the screen. Okay, okay. So today we continue. Okay, before that, let me know what we have learned before. Okay, we learned before we conclude our presentation, our class lecture last time. Okay, the last thing we learned is about the thermal voltage. Okay, which is thermal noise. Okay, thermal noise where the thermal, it will produce some electron, some conduction, whatever, because when the thermal, the temperature is increased, the electron will start to move. When electrons start to move, that means there will be some undesired current flow. Okay, so it is not intended, and it is due to thermal. That's why we call it a thermal noise. And this is the initial one. Okay, the initial one, the Rn and noise. Then we try to make equivalent circuit out of this noise source. So we have in terms of Thevenin equivalent circuit, we have Vn as the voltage of noise, and then we have the resistance of the noise. Okay, the Rn. Okay, noise free, this one. Okay, so noise source will be connected to system with the input resistance RL, and for maximum power transfer we will make Rn is equals to the load of the resistance. Okay, so this is what we call as a impedance matching. Okay, so then you from the Thevenin equivalent circuit with the loads here RL. Then for maximum power transfer, Rn is equals to RL. Okay, R noise is equals to R load, equivalent to one value. For example, Rn equals RL equals to 3 ohm. So this one is for maximum power transfer. If the question maybe ask you maybe not maximum power transfer, maybe so means that the RL is not equivalent to Rn. Okay. Normally, we want maximum power transfer. So means whatever we have here will be transfer 100% to the load. Normally lah, we want maximum power transfer. Okay. And then to calculate the voltage across VL, okay, across RL. So it's just current, it's just voltage divider because it is a series connection. So RL over Rn plus RL Vn. Okay. And then because they are the same value, that's why 1, for example, if it's 1, 1, 1, 1, so 1 over 2 Vn. That's why it's divided by 2 because it's the same value. Okay. Then you learn how to do the power, which is P equals to VL square over R. So VL square is actually Vn over 2. So that's why we have this number, this kind of representation. Then we have Vn square over 4R. Then we have to relate with our KTB. Okay, we learned before before there is n equals to KTB. So KTB is equivalent to Vn square over 4R. Then we get Vn equals to square root of 4 KTBR. Remember, for the value here, Vn here is actually Vrms. Okay, Vrms is actually Vmax over square root of 2. Okay, this one we have done it. Okay, so today we go to the new parts, okay, which is the noise, okay, which is the extension of our still noise, okay, because this chapter is about introduction and noise, okay. Okay, noise effect can be determined by measuring signal to noise ratio. Normally, we want SNR to be high. Okay, normally we want SNR to be high. Why? Because we have signal to noise ratio means it's a ratio. Then you have signal. Then we want to have noise. In order to get a good SNR, so the good SNR is the one with higher SNR. So higher SNR can be achieved by having higher signal, or or by having low noise. Okay, given that for this condition, given that noise is fixed, we increase the S, we will get a good SNR. Given this is fixed for the second condition, then we reduce the N, so we still get a high SNR. Okay, it's just a ratio. Then the next is probability of error. Okay, this one is for the digital system. So whenever you hear bit error rate, that is a digital. Okay, so SNR not, okay, output is always less than SNR inputs. Okay, I think it's logic. What we send back, normally what we receive is much smaller. Before you amplify lah. Okay, so uh, so it's logic. Okay, there. If you don't understand, you let me know. Okay, due to the extension of noise in the receiver itself. In the receiver, usually a constitute of process. Okay, when we receive a signal, we have few process. Okay, you will learn throughout the subsequent chapters later on as well. Okay, receiver usually constitute a process of filtering, demodulation, and amplification. Okay, when we receive signal with the carrier, we will remove the carrier at some point because we only want the information signal. So that's why sometimes we require filtering. Okay. Okay. Other parameter that can be used as noise factor F and noise temperature E. Okay. So SNR is a ratio of signal power. Okay. S to noise power N. Okay, here. Then you have a noise factor. Okay, you see the word here, noise factor and noise figure. Okay, so depends when you write in your exam properly, clearly define to us which one is which, because sometimes if we ask you noise figure, mean it is in decibel. So you need to produce answer in decibel. If we ask about noise factor, it is actually in linear. Okay, so please make distinction. For me, I know. For me, it depends on person. For me, if noise figure, I write an F, and if for factor, I will write F. Some people maybe use small f and big F. Depends on you, but at least we can know what you actually are solving. Okay. For me, I'm still okay, but I'm not sure with the other. For me, as long as I understand what you are trying to answer, then it's good. Because when you answer this, let's say we ask noise factor, but you put using F, but you answer using log, means your answer still wrong because you are asking about noise figure. Okay, so for the noise factor, F is actually a ratio between SNR input over SNR output. Okay. Wait, I end this show. Discard. Because I want to share the other screen. If you don't understand, please interrupt me, because I cannot see the Webex chat properly. Okay. Stop sharing. Sharing of the screen. Okay. So that is a noise factor. Okay, we have a noise factor. Then we have a noise figure. Okay. So noise factor is actually SNRI input over SNR output. Okay. So because SNR itself is actually ratio, so it's actually SI over NI over SO over NO. Okay. This is division. So SI over NI divide by SO over NO. Okay. And if we convert this to multiplication, we will have SI over NI and NO over SO. Okay. Then you have SI NO over NI SO. Okay, NISO. Okay. So noise figure is just actually the 10 log. Okay, 10 log of your noise factor. Okay, this one. Okay, or this one, for example. Okay, so let's say this is division. So you have a 10 log. Sorry, 10 log. Okay, we take this one. Okay, if you want to separate it, what it will happen? If you want to separate this into two, logarithm. So what will happen? Is it minus multiplication or what? Can you answer me in the WebEx chat?
Minus.
Minus, right? Who answered it?
Basta.
So it will be minus, right? So it will be minus here. Okay. So thank you. Page 31. Okay, this one look like a lot because I didn't remove the things. Okay, so this is 31. Okay. And then we have this one is actually if you want to calculate each of S and R lah. Okay. You have 10 log over S over N. Okay. Then you go to the next one is amplifier. Okay, amplifier is actually okay. I know you see this face wait pen okay, it's okay as long as you see what I want to do okay. to sim to simplify the analysis, the following noise model is used: amplifier with the noise. So actually even the amplifier device have their own noise. As you learned before, right, we have internal noise and we have the external noise. Okay, so this is calculation. This is a noisy amplifier, means apply amplifier with a noise. So you have NI, because now we are calculating noise. We are calculating noise. That's why we are, you see, we are referring to noise. We didn't refer to the signal. Okay, we are calculating only the noise now. So this is the input noise. Okay, means the input, the noise that present before the amplifier. And G is actually the gain of the amplifier. And NA is actually the gain, sorry, the noise inside the amplifier. So this is the external noise that being fed. Okay, we not intend, but it exists anywhere. And then we have NA, which is actually the amplifier exists inside, the noise exists inside amplifier. Then we have a gain. Then this one is the output noise, means the totality of the noise that we get a combination from the input noise and also the noise from the amplifier itself. Okay. Then if we want to separate this for easy calculation, so we take this NA out. Okay, it will become here NE, and then the gain, purely gain, and NO. Okay, so when we take it out, NE is actually equals to NA over G. Okay, NA over G. Okay, because we need to divide by the gain, because when it take out from the amplifier means that it's not going to be amplified yet at this point. Okay, this when we put it here, it's not being amplified yet. But if it's NA inside here, means it's already amplified by gain. So NA actually equals to NE with G. Okay, noise in the amplifier, this one is the noise from the amplifier, but we take it up. Okay, so that's why you have this equation. Okay, and then we learn also from Pn, the one that we learned last week. Okay, Pn equals to Ni equals to KTIB. Okay, Ti is actually the temperature here. Okay, so it is in Kelvin. So when we want to convert from Kelvin, for example, temperature in Kelvin is actually temperature in degrees Celsius plus 273.15. Okay, and you need Kelvin. And B is actually bandwidth. Okay, means the higher bandwidth, for example, USB upper sideband minus F lower sideband. Okay, then we get a bandwidth. Okay, and then K is a Boltzmann constant that I asked you to search from your calculator. Not sure you already search it or where you managed to find it. Okay, so this is the K lah. And then from here, you see, to get the noise from this figure, okay, from this figure to get a noise is actually G and I plus NA. Okay, or NA can be replaced with this, right? So you have NO equals to G N I plus NE times G. Okay, so this is the output noise. Okay, the noise that we receive at the output, combination from the input noise that given to us, and also the noise comes from the amplifier itself. How to see the chip? Okay, so far okay. If okay, say okay inside the web chat. Because it's how I'm going to see you guys here. Okay. Okay. If you okay, just say okay, because how to is checking. Put it out. Okay. Okay. This next we going to analyze. We go next going to analyze the amplifier noise. Okay. So if you notice, this is SNIR over SNR naught. Okay, this one is actually our for example our noise factor, because figure is in decibel. Okay, maybe I next this cut, because I want to show you new slide. Okay. So how I'm going to see at the same time. Okay, so we have F. Okay, never mind. I will use pen. This one I will take, copy. One. I feel sleepy. I don't know. Is it only me? Because it's evening class, right? It's already feel like so sleepy already. Okay. Then I put here first. Okay. Not sure student need or not, but you already have slide with you, right? So you can jot down yourself. Okay. Okay. So the next one is actually the analysis of amplifier noise. Okay. Okay. I put here first this line, and then this one new pages. Okay. So now we're going to analyze the amplifier noise. Okay, the amplifier noise. So we have the amplifier. Okay, this is your amplifier, and then we have output. Output for sure we have a signal. Okay, the output signal, and also the one that we don't desire, which is our output noise. Okay, then we also learn that this is the signal Si, and this one is the another noise before the amplifier. So it is actually Ni plus Ne. Okay, like we learn which one is from the outside, which noise exists from the outside, and which noise actually exists from inside. So Ni is from the outside. Okay, and Ne is actually the initial that inside the amplifier, exists inside our amplifier. So if we want to measure the F noise factor, so it's actually S and R I input over S and R output. Okay. So for S and R input is always Si over Ni. Okay. And then for the outputs, okay, you can just times. Okay, times you will have N. You have N output over S output. Okay. Then you expand again. Okay, you expand again this how you get NO and how you get SO. You can further expand them. Okay, let's say you don't disturb SI and I because that is the most simplified one. Okay, then you try to obtain, for example, the NO over SO. Okay. I want to see your slide have shown it on I. Okay. So for here is the total noise. For here is the total noise is coming from the outside and coming from the coming from here. So G gain, and then noise is actually Ni plus Ne. Okay, external and internal inside the amplifier, and then we have S naught. S naught we actually just a gain of Si. So we have S naught is actually GSI. Okay. S output signal is actually the gain of input signal, and then to get the N output, okay, output noise is just gain Ni plus Ne. Okay. So if you see this, we can do cancellation. Si can be cancelled with this, and G can be cancelled with this. So ended up you will have 1 over Ni plus Ni over Ne. Okay. Then further simplify. Okay, for the noise factor, Ni over Ni is 1. Then Ne over Ni. So this is the most simplified answer for the for the uh, for the noise factor. Okay, should we ask you noise factor? If we ask you for the noise figure, then it's a 10 log of this. Okay, if we ask noise figure, it's actually 10 log of our F. Okay, so I take this also in case student need. Okay, So finish with that. Then we try to relate. We try to relate with our temperature. Okay, our temperature. Okay. New. Okay. So the next is actually temperature. Temperature means we can measure temperature as well. Okay. Because temperature is one of the noise. We need able to measure the temperature lah. Okay. So if we have just now F in terms of noise power, we have 1 plus NE over NI. The one that we already derived just now. Okay. So if we want to relate with our temperature, okay, F equals to 1 plus TE over TI. Okay. The temperature exists inside the amplifier, and this one is temperature before the amplifier, TI. Then after that, if we want to rearrange, okay, rearrange with, let's say we want to know the temperature of the amplifier, so it's just another rearrange. So Fe equals to F minus 1, okay, F minus 1 and Ti, okay. So this is if we want to involve the value of temperature. Okay, and then for the noise factor in terms of temperature is 1 plus KTEB over KTIB. Okay, because this is the same, okay, because KTB is the same, that's why we cancel out. Okay, we cancel out and we cancel out B as well. So that's why you left with still FE equals to 1 plus TE over TI. Okay. So this is your noise factor, okay, in terms of noise factor in terms of temperature. And this is your noise temperature. Okay, this is noise factor. This is noise temperature. Okay, noise factor. This one is noise temperature. Don't mix up. Okay, next. Okay, do you, sorry, Dr. TE is for what? Oh, TE is actually, okay. If you see here, okay, Abdullah Morad, okay, if you see here, where, wait, if you don't understand, just interrupt me. Don't ask in Webex chat because I don't read. This one constantly I read because difficult to split screen. If you don't understand, just say directly. Don't shy. Shy will not get you anywhere. But it's okay. I read just now. Okay. So an E is actually okay. Initially we have an A, which is the noise exists inside amplifier. And then in order for us to take it out, okay, the noise inside amplifier, we want to take it out so that they are here instead of mixing one inside and one outside, one noise outside, one noise inside. So we take out the noise factor inside amplifier as an here, as a part here. But when we take it out, we need to do a ratio, okay, which is NE equals to NA over G, okay. Because in order to get the Na here is actually Ne times G. Okay. So this is the same as the temperature. So Te is actually the temperature that initially inside Ta, then we bring it out, become Te. Understand?
Yes,
This one
yes,
is
Doctor.
power. Okay.
Yeah, now it's clean. Thank you, Doctor.
Okay. Okay, welcome. Where was I? Okay. So so this is the noise generated in amplifier of 5 megahertz bandwidth is represented by amplifier. input noise power of 0.082. Okay. Calculate noise factor and noise figure if the amplifier was fed with the source input signal match the temperature of 300K. So we have input signal power, okay, which is Ni equals to 300K. So it's already in Kelvin. And then noise generated in amplifier. Okay, the word here, you see here? Means is it, okay? So is it NE or NA? You see here, the noise generated inside amplifier means it is a NA, okay? Inside amplifier. So the wording up, please read carefully. Noise generated in amplifier of 5 megahertz bandwidth. So this is B, your bandwidth. Is represented by amplifier input noise power of 0.082 picowatt. So this is noise input power. So NI, okay? NI. Calculate noise factor and noise figure if the amplifier was fed with the source input signal. Okay, now try to do 3A. Okay, then I will pick your name. Just try to do first. I will pick your name and you will share your answer inside Telegram. Okay, just try to do answer 3A first. Slow and steady, okay? What can I do here? No, because I want to make this one bigger. How? Can you see your own slide? You have your own slide, right? So I give you around 10 minutes. Slowly. Okay. Oh, I cannot make this one maximize because it's initially slow. So refer to your slide. Try to do 3A only. 3A only. Slowly, yeah. So 325 until 335. Okay, unshade the screen. Unshade the screen. Stop sharing. Okay, I stop sharing so that you can refer to your own your own PowerPoint, which is much clearer. Okay, and the one that I shared to you. Okay, so the question asks noise factor mean F, the linear, and then we ask about noise figure means in decibel. Okay, so two things that we need to solve there. So we